Hi, I'm going to look at TRANSUM Release 9 and its support for SMB2, and I'm also going to use the opportunity to explain the differences between the response times measured by Wireshark and the response times measured by TRANSUM. So here we have a trace open, and over in the info field here we see SMB2 requests and responses. I've also included the message ID column so that we can match requests and responses should they all get out of order. Now what we notice over here is we have the this is SMB2.time. This is the time from request value that's generated by Wireshark, and here we have the APDU time generated by TRANSUM, plus the service time and the spread values as well. But let's just concentrate on the APDU response time. You can see that this value matches the Wireshark value in all of these cases as we come down this trace. And sure enough, if we go and look at a multi-packet message, so let's just skip forward. Here we have a message 696, it's a read request, and the response arrives just here. So here we can see again that the APDU time is the same as the time generated by Wireshark. There is this additional information though. TRANSUM generates this value called service time, and the service time is measured from the last request packet to the first response. And in this case we only have one request packet, so it will be measured from that point. And you can see that it's measuring just between this packet here and this packet here. And then the time taken to send all of these packets is allocated to a value called response spread. This is how long it took to transmit all that data across the network. And of course this could be affected by things like retransmissions, TCP window sizes, Nagel algorithm problems, all sorts of things, overload of network links and high latency, etc. So this gives us a slightly more detailed split of this time, but the Wireshark time is still good. It still all looks good here and all matches up. And for this trace and for my Wireshark configuration, I've left it to default with a TCP setting called TCP sub-dissector reassembly, and that is enabled. That's a nice easy thing to remember, but by default that's enabled. It just means, in practical terms, it means that the summary information appears on the last packet of a sequence of packets. That's why we see a sequence here and a final packet. So that's the way we've got Wireshark configured. Now let's take a look at a slightly different trace. In this case you can see we've got the same sort of thing. We've got a close request here, and there's the corresponding close response, and you can see that this value here matches this value here. It's been rounded to the nearest microsecond, but basically they match. This value here matches this value here, this one here to this one here, and they all match. So again, no surprises there. The values in Wireshark look exactly the same as the values from TRANSUM. Now let's go and look at a particular sequence of packets. Now here we can see a write request, and in fact the write request is actually in a packet with a find request. So we have a write and a find bundled together, and here's the write response and here's the find response, and the responses are split. Now if we look at the APDU time in this case, the value is vastly different. So the APDU time here is 975 milliseconds, and yet even if we go to the last of these responses, and TRANSUM always measures the last response to come back, so it gives you worst case. But even if we look at these values, we still only have a value of 342. So there's a vast difference, but the service time is very similar to this time. And we can see that we've got this really big request spread. Now the reason for that is because this write request is actually split across lots of packets, because we're writing a load of data across the network to a share, and then eventually the last packet of that sequence shows the summary information. And TRANSUM has correctly measured from the first request to the last response and said that that whole sequence takes 975 milliseconds, but Wireshark is only reading from the last request to the last response, and so we've missed all of the packets that preceded this packet number 1633. So that's the big difference between TRANSUM and Wireshark measurements of values. You can get Wireshark to correctly measure the write command by changing the TCP subdissector setting, and if you change it to say don't allow the subdissectors to reassemble segments, if you switch that setting off, then the write value will be correctly measured, the response time for the write command. But unfortunately, the read command that we looked at earlier, that will then suffer a problem where it won't cover all of the packets that follow the first response packet. So whichever way you set that setting, one way or another, it's going to be wrong for either reads or writes. And that's also true for HTTP and other protocols where Wireshark provides you with either what it calls time from request or time since request, it sometimes calls it. One thing I wanted to show you here, it would be a lot easier if we could see this information on this line here, or actually on this line here for the last response. Now we can do that by actually changing some protocol preferences. So I'm going to keep the information on the last request packet. So I set that, and that means that this doesn't change, that information is still there. But I'm also going to add additional information to the last response. And now you see that we have the value actually split across, it's actually showing on both of the response packets, but now I can quite easily do a comparison. This wasn't so important in this case, but if you had hundreds of packets between this point here and the response coming back, it would be fairly painful to keep having to page backwards and forwards to look at these. So that's quite a neat additional facility in TRANSUM, this ability to place the RTE data on any packet you desire. Thanks for your time, and I'll see you soon.